All right. Welcome, everybody. Good morning, good evening, good afternoon, depending on where in the world you're joining from. People are still rolling in, but we're going to go ahead and get started here because we only have 1 hour ahead of us. So, that being said, there are a few housekeeping things we need to get started with before we get going with the webinar. I want to encourage you uh, to minimize the number of applications and programs you have open on your desktop right now or whatever it is that you're joining from. If you have any questions, and I'm pretty sure people are going to have questions throughout this webinar because the cadence is going to be pretty fast, please leave them in the chat. We're going to address all of those or as many as we can in the last 15 minutes. So please, yes, please use the chat feature to send any questions or any concerns that you have. We are also letting you know that this webinar is being recorded for us to be able to distribute this session for people that registered but couldn't join, or for people that would just want to watch this webinar second or third time. If you experience any issues, there's an email that you can use on your screen right now. So with that in mind, what we have ahead of us is 45 minutes of essentially me going through a very quick introduction in Python scripting with Abaqus. It's by no means going to be a comprehensive and complete list of everything you need to know about Python scripting, but should hopefully get you more confident in getting started with it, depending on your prior experience as well. And the last 15 minutes, we're going to reserve those for questions and answers. So with that out of the way, I will start with another presentation in just 1 second over here. So making sure everybody sees that. So before we get started with the webinar, I'm just going to quickly introduce myself. I got my diploma in mechanical engineering. I'm a mechanical engineer with the bachelor and master's from University of Thessaly in Greece, and then pursued graduate studies at Harvard University studying the nonlinear mechanics of mechanical metamaterials and soft actuators and soft robots. Ever since 2020, I joined Verist Engineering, and I'm a solid mechanics simulations expert at Verist since. I'm also one of the first worldwide recipients of the Abaqus Structural Analysis Associate Certification by Dassault Systems, and excited to meet you all here virtually and talk about one of my favorite things to do with Abaqus, which is how to utilize scripting, Python scripting, that is, to make your workflow more efficient, enable new functionality, a lot of things that we're going to talk about. Now, as I mentioned, I'm a solid mechanics simulation expert at Verist Engineering. At Verist Engineering, we help our clients create extraordinary products through multi-physics simulation, failure analysis, but also material testing and modeling. Very quickly, I want to talk about who we are. We were founded in 2006. We currently have 18 staff. We are strongly motivated and enthused by the use of physics and chemistry through fundamental engineering science. We provide academic level expertise applied on an industrial time frame. On your screen right now, you see a couple of examples that we have as part of our case studies on the website. More specifically, in this slide, I do assume that the majority of the people joining here are interested in solid mechanics. I'm just going to pause here for a second and kindly ask everybody to mute themselves. Thank you. So the majority of people joining, I assume, have a solid mechanics interest or solid mechanics background. So the problems we solve on a day-to-day involve nonlinear materials, large deformation, impact loading, adhesion, debonding, contact failure, couple physics. We also do in-house testing. to determine material properties, and also validate our simulations. But we also do material model calibration on top of that testing data that we obtain, so that we can accurately model our materials in our finite element simulations. We also offer seminars and paid classes on top of our free webinars, which is this one, such as this one. Um, Before we get started with Python scripting, I just want to put out a schedule for free and paid classes that we have lined up for this year, all the way to September. You can see those on your screen. The first one is what you're logged into it right now, the Introduction to Python Scripting webinar. As you can see, we offer various topics. So if any of those are of interest to you or any of your colleagues, make sure to sign up through our website for the free ones or the paid version ones. We also have in-person paid classes. And if there is something you want covered that you don't see here, there might be the possibility that we cover that in the future later this year. So with that out of the way, let's get started with our webinar here. Talk about Python scripting. One of the things I want to answer to people is, why would we even bother about Python scripting, or what do we gain from it? And as with most tools, as you use them, you tend to uncover new functionality that applies to yourself. But here I'm going to talk about 5 reasons on why I think Abaqus scripting, Python scripting with Abaqus is important, particularly to me. First, it's what I call version agnostic. So Python scripts that we develop or that we create with the help of Abaqus do not care on which, for the most part, do not care on which version of Abaqus they were created. Unlike Abaqus CAE versions or Abaqus CAE models that you might have experienced, as soon as you upgrade to a newer version, you save your CAE file. That CAE file can no longer be opened with the previous Abaqus version, even if it's the exact same model. Now, this is something that might be addressed in the future, but does not apply to Python scripts. If you have a Python script that creates a model and does something with it in Abaqus, you can run that script on any Abaqus version, as long as you're not using any functionality that was not implemented in previous version. There is a caveat to that. Abaqus 2024 has now started to support Python 3. So there might be some slight modification to your Python scripts before you're able to use them with 2024, or vice versa. But the idea here remains that Python scripts are generally version agnostic. So that's one strong reason why you would need to use them. The second is that they are very compact containers. The model information that we store in the form of Python commands is significantly more space efficient. It's essentially code. So as big of a code file as it can be, it's always going to be smaller than a CAE file. Now, this is for a good reason. The Python script that accompanies an Abaqus model is not the model itself. It's rather the recipe, a series of commands that can recreate the model. So for this reason alone, it's very efficient storage of information. You're not storing the entire model, you're just storing everything needed to recreate it. So that makes it very convenient to share with other people, or to store it somewhere so that you can go back to it later in the future without having to store the entirety of the model. A third reason is reproducibility and parameterization. Now, depending on how seasoned of an Abaqus user you are, you might have experienced, setting up a model, building up a model, and then realizing either that you made a mistake and you need to adjust something, or that you need to modify, let's say, a dimension or your part, something that needs modification, and then you're thinking to yourself, oh, I need to redo everything I've just did up to this point. And that's what, at first, that's annoying, but it's also dangerous, because as we tend to do repetitive tasks, we tend to be less and less focused and careful. So Abaqus scripting can help with that, in the sense that if we parameterize a script to work with arbitrary dimensions, then any commands, any actions that we have done to create the model can be run automatically. Particularly the tedious and repetitive ones, such as creating sets, surfaces, defining the mesh, partitioning our domain, everything that we need to do. We can do it parameterized in a parameterized way, in a very reproducible and error-free way, by using Python scripting. Next is post-processing. That's the fourth reason. Apart from creating a model and setting it up in a parameterized way that you can all do with Python scripting, another thing that we can do is access the output database to quickly extract and save results, or generate plots and movies, whatever it is that you want to do. You can also do more advanced things with post-processing, such as creating custom field outputs that are not already available to you. So that's a fourth reason. The fifth reason is new functionality. So I put this in very broad terms here. Take it to mean whatever you can make it mean. But I'm gonna give a few examples here. So with the use of Python, we can enable new functionality that is otherwise not accessible with just the CAE or the input file. A few examples might be implementing periodic boundary conditions or solving inverse problems. Periodic boundary conditions, for one, they're not there's not a button for periodic boundary conditions in Abaqus, and implementing them properly involves thousands and thousands of constraints that one needs to introduce. So it's impossible to do it without Python scripting in an automated way. Solving inverse problems is another. And now with Abaqus supporting Python 3 in version 2024 and onward, we have the capability of loading in packages anywhere from even machine learning packages, or curve fitting packages, mathematics packages, plotting packages, anything that you can imagine. So as you become proficient with Python scripting, that new functionality, you can make it mean whatever is more appropriate to your workflow. So these are 5 reasons why you should even bother to consider scripting in the first place. So hopefully that motivates you to continue investing time in learning how to use Python scripting with Abaqus. Let's see how Abaqus already provides us a few ways to get started with Python scripts. The first form of file that you might have encountered or might not are environment files. So these files have an env extension. These contain Python commands to more or less set CAE environment properties, licensing information, and much more. If you haven't opened one of those files, I suggest that you go and see where those are in your Abaqus installation, see what they do. If, for example, every time you open a CAE window, you tend to change the graphics background to a different color, let's say, you can add that command in your environment file, and it will be taken care of automatically every time you open a new user interface. So that's the first kind, perhaps the simplest kind. So Abaqus is already relying on Python commands in the background to set up things and get running. The second kind, which is probably more appropriate to what we're doing today, is journal files. So every time you save a CAE file, you might have noticed that there's always a file with a JNL extension using the same name. There's no way to prevent that from happening. That always accompanies the CAE file. The journal file contains Python commands, and these Python commands are used to recreate the CAE file in the event of a crash. So it's always good to keep those together. If you're sharing them with somebody, keep the JNL file together. This is a great resource to get started with scripting. So open up a JNL file that accompanies a CAE file that you already have. See what's in there. It might be a lot at first, especially if we're talking about a very big model, because it's going to have a lot of commands that you don't recognize, and you might think, oh, what is this? It's too complicated. So it can be very difficult to understand for very large models, but if you start with very small models and try to read through it, which is we're going to do shortly here, this can be helpful to get started with scripting. Another form of file that Abaqus provides are replay files. Now, every time you start a session, a CAE graphical user interface session, Abaqus will automatically create an RPY extension file, which is essentially a carbon copy of anything you do on the user interface. If you zoom into the screen, you rotate the view, you open up a CA file, you close the CA file, you open up another one, it's going to record those commands in the form of Python commands. So this is used to restore progress even if you don't save a CA file, and it's also going to be used to across CAE files, and even if you don't save them. So if you've noticed, every time sometimes your CAE crashes and you open it up again and it says that it discovered a restore point, and it asks you whether you want to reset to essentially where you were from. It's using the replay file to do that. Um, Even though this is also a resource, it's perhaps too verbose to rely on. So if we are opening up an RPY file, it can, for most people, it can be way too much to be helpful, because it's recording things that we don't really care about for scripting, such as zooming in the view, rotating the view. We don't need things like that. Moving on with a few basic things, and then I'm going to end with a presentation, and I'm just going to go directly to a CAE window so we can see these things in action. Um, Abaqus uses Python, particularly the object-oriented Python, if you've heard that term, uses dictionaries and objects to store all model information. It's important for you to know that Abaqus already has a structure for how things are stored in place. So this is, I guess, the most difficult aspect to get started with scripting, because the user doesn't know this structure by heart. So the first time you get introduced to it, you get exposed to it, it might seem like a lot. But we're going to show you a way on how to get started here so that this doesn't look too overwhelming. Um, an example here is that a model, the basic model that you might be using on a day-to-day on a CAE window, is stored in the form of the command to access it is mdb, which stands for model database, dot models. Models contains all of your models in a CAE window or a CAE file. Model 1 is the model name. Dot parts returns a part object. Um, so these so mdb.models and mdb.models.parts are both dictionaries containing objects. So dictionaries in Python are very efficient containers. Abaqus is using a lot of dictionaries in their scripting form. Now, the difference between dictionaries and objects is that objects have properties, so embedded variables and methods that we can use to perform actions. How can we distinguish between the two? Um, there's a convention here that Abacus sticks to, which it's not necessarily observable the first time that you see this, but it's really helpful to know. Um, Anything that uses a lowercase name is representing data structures that have already been created. So a container, for example. So you see models here is lowercase. So all of the models have already been, the model container has already been created, and it contains model 1. There are parts already created. So dot parts is lowercase, so p is lowercase, and part 1 is one part within the part collection. In contrary, whenever we want to create something new, um, that that is by convention is going to be uppercase. It's going to be starting with an uppercase character, and it will denote that a new data structure is being created. For example, whenever I'm creating a new part, you see that everything at the beginning of this remains the same, but the dot part is now uppercase, indicating that I'm using a method called part, to create a new part, and I'm providing some arguments in there to hopefully define how I want to create this part. So this is a subtle difference, but it's important to know so that you can make sense of, why we're using this versus this, and why Abaqus is using one versus the other. Um, the last slide here is one of the most useful commands when you're scripting, which I'm not going to ask you to memorize. I'm going to show you what it does in action. But it essentially, if I'm going to preface this anyway, is that this command allows us to make sense of the commands that Abaqus will write for us in the scripts. If we forget to put this command in the user interface, whatever commands are written are not going to be very helpful to us to essentially modify. So let me exit from this presentation and show you what I mean by that in action. So I'm going to drag this window over here, and I'm going to open up a file that I already have. So this is nothing but a 2D square that I've already defined. Nothing really to it. I'm just opening it up, and I'm gonna start something new. I'm gonna do a new action, and I'm gonna go and look what is the command that Abaqus wrote for this, and see whether I can make sense of it or not without putting this command that I just showed you. So first of all, let's remember what we just said. One of the ways we can find Python commands is in the journal file. So I know that when I save this, it will automatically create a journal file with Python commands in it. So that's where I'll go and look. But before I do that, let's make something new. I'll make a new set. I'll go ahead and create a new set. Doesn't really matter what name I give it. I'll select this top edge over here, and then I'll actually save it as a new name, with a new name, square 2. All right, so then I am going to drag this window over here. You're going to see I just saved square 2, and there is square 2 JNL. I'm going to open this file and see what's in it. So I'm going to drag this window over here so that you can all see. There's no highlighting over here, but all we care about is the last command that it was written. This command over here. As you might recall, I just made a set. I created that set by selecting an edge. And if I go and look, what is the how does Abaqus indicate what is the edge that was selected? It's using something that says get sequence from mask. Now, I don't understand what this is. It says something like number 4 in here. This is an internal Abaqus way of identifying objects and where they are in space. If we wanted to parameterize this and want to change the dimensions of our square and the location of that edge will change, the number 4 might remain the same, but it's not helpful for us to parameterize this in terms of geometry. We want something that has to do with geometry here, as opposed to get sequence from mask. So this is exactly what this command that I showed you earlier takes care of. So if I want to put this command in here, what I'll do is I'll go down here and change to the scripting view, to the command line interface, and I'll just autocomplete my way doesn't want to autocomplete for me, so I'll just copy that command directly from my scripts. Let me just take it from here, Session journal options, set values. All right, so I put this command in here. I executed it, and now I am going to make another set, just like I did before, with the top edge. I'm going to make it one more time, and I'm going to save it as square 3. And now I'm going to go back to the same folder and open up square 3, the general file for square 3, and see what's written in there. So as you can see, there is another command in here that I'm just going to separate it to make it more visible. And that command is now different. Even though I just created the same set with the same edge, the structure of the command is different in the sense that it's using geometry now, X, Y, and Z coordinates to indicate where that edge is located. This is significantly more helpful. This is something I can use. I can parameterize. I can change these dimensions to whatever I want. So this is what this command is doing. It's forcing Abaqus to use geometry or coordinate values to denote anything geometry related. So this is something that we need to do. If we forget to do it, it's everything that's going to be written in our script is going to be of this form, and we can't do much with it. So with that out of the way, let's discuss a few other ways that we can discover Python commands, because as I said in the beginning, there's already a structure. The commands are already there for us to create geometry or use the commands to our assistance, but we don't know what these are. And the general file might be one way that we can find those commands. I'm going to show you another way, perhaps the best way to get started with it. And that's with macro commands. So if I go to File, Macro Manager here, I can see that this window pops up. I can go create in my working directory. And this window starts up here. It says record macro, and there's a button to stop recording. So all this is going to do, it's going to record the Python commands necessary for me to do any action that I'm doing until I press stop record. So let's go ahead and define, let's say, a new material. I'm going to go over here, define a density, and I'm going to give it some elastic constants. Response ratio. So I define the material, and let's also create a section. Let's create a solid section with that material. Let's say material number 2. And then I'll stop the recording. Once I stop the recording, I can go back to my folder structure, and I can try to look for a file named abacusmacros.py, which is this file over here. This file will contain all of the macro commands I've written. You see I've written quite a few. The last one is the one I just recorded. So as you can see, it defines the macros in the form of functions. Each of them has some imports that are necessary for this to work. And then there are the commands that essentially correspond to the actions that I did ever since I started recording. If we read through those, the first 2 have to do with the session viewports. So they have to do with what's visible on my screen. So as far as, reproducing this action, these are not necessary. We might delete those to make this simpler. This is the command that's useful. It's creating a new material. It's assigning that material a density. It's assigning the material elastic constants. And it's also creating a section and associating material number 2, which I just created, with that section. So now that I have this over here, let's say I want to modify it. Let's let's say we want to modify by giving it a custom density, a custom Young's modulus, and a custom Poisson's ratio. So we provide these three arguments to our function, and we're going to go over here and change this to our density, change this to whatever Young's modulus we provided, and whatever Poisson's ratio we provided, uh, so that we can make a custom material. And let's also provide a name because we want to make that material unique. So material name, and I'll go over here, select material number 2, and every instance that is being shown, and change it to name. Actually change it to M name so that it doesn't get confused with anything else. Everything but this. So that should be all set. I'll save this, and then I will go back to my CAE file, and I will run that script. I will go File, Run Script, and I will go here and select my Abaqus macros file. I run it. It looks like nothing happens. Just to verify that nothing happens, I'll delete those two materials that I have, and I'll also delete my sections, and then I'll run it again. And as you can see, I still have no materials and no sections. This is for a good reason. This happened because when I run this script, I run this file, I'm just loading in the function definitions here. I haven't actually called those functions yet. So I'm going to do just that over here. So I'm going to call macro3, which is the command creating our new material and our new section. And as we remember, it needs a material name. So let's call it material new. And then we need a density. Let's give it the same density as before. And let's give it something drastically different so that we know this worked. Let's give it a Young's modulus of 10 and a Poisson's ratio of 0.1 or 0.2. Let's run this. And if we go here in our tree, if you see my cursor, we see we have a new material with the density I provided, the Young's modulus I provided, and the Poisson's ratio I provided. And we also have the section assigned with that new material. I can go ahead and run this again with, a different Young's modulus and Poisson's ratio, perhaps also a different density. Run this over here, and if I go to the material, the density has changed, the elastic modulus has changed, and the Poisson's ratio has changed. So it's very convenient to make changes that way. But what I want you to keep from that is that Macro Manager is perhaps the most helpful way for you to get only the commands that you need to figure out, how do I get the commands that correspond to this action and this action and this action. So hopefully that makes sense. You can use this, and as you get more proficient with it, you can start doing more and more actions with each recording and each macro, or you can customize it to specific actions that you want to perform. For example, whenever you open a file, you want to do some definitions every time, you can record those in a macro and just run that macro every time, or you can copy what's in that macro in your script. So with that out of the way, let's clean up our model database. That's the command I just put here in the window, mdb with an open parentheses, cleans up the model database. It's equivalent to me going file new model database with standard explicit model. So what I'm going to do next in the remaining 10 minutes, we're not going to have the full time to do this, but what hopefully I'm going to do by showing you here is try to create a structure like this, where scripting will be extremely helpful. This structure is a perforated structure, so you can imagine this is a 2D square with an array of holes that we take a bunch of circles and we perform cuts in our rectangular rectangular sheet. And then what's interesting about this is that for certain cases, if we subject this thing to compression, we get a nonlinear buckling style behavior where the holes become ellipses and the orientation kind of alternates, as you can see here. There is a nonlinear force displacement relationship for a structure like this. But what's interesting about this is that this doesn't happen for any number of holes, any size of holes or ligament size. The behavior of this structure is strongly dependent on how many holes you have, what's the width of those ligaments, how many holes you have in the X and Y direction and stuff like that. So it's an interesting exercise to consider this structure and be able to very quickly modify how many holes I have in the X direction, how many holes I have in the Y direction, run the simulation, set up everything I need to do, my scripts, my boundary, sorry, my sets, my boundary conditions, my material assignments, my mesh, everything. I want to be updated. I want everything to be updated at the same time, very, very quickly, without having, to define the model from scratch. This is where scripting comes in handy. So this is what we're going to try and do right now. So there are many ways that one can go about this. I'm going to show you one, which I think is the easiest. I'm going to start with a 2D square over here. So I will do 2D shell, approximate size 1. I'll create a square at 0, 0, and 1, 1. So here's my square. Click done, and then I'll make a circle. Part 2, given that my square is size 1, I'll make my circle slightly smaller. Let's make it like this. And then what I can do is I'll go to the assembly and I'll create an instance of each. As you can see, my circle lies here in the corner. I'll make a couple more circles. I'll make let's say I'll make another one and then another one. So I'm not creating new parts because I don't care about having different parts for different circles. I'm just creating different instances of the part. So as you can see, I have 3 circles over here. Let's move those a little bit, shall we? Let's get the second one. I'll translate it by, let's say, 0.25. That looks good enough. And then I'll also translate this one by 0.25 in the vertical direction. And then what I'm going to do is I'm going to create a cut. So I created a cut here, cut operation, which says select the instance to be cut. So I want to cut the square, and the instances that will make the cut are the circles. So I do this, and as you can see, I'm slowly starting to create the structure that I showed you before with an arbitrary amount of circles in the X and Y direction. So I want to stop right here before I get too much in depth. And I want to see what the commands are that correspond to what I've done up until this point. So to do that, I'll save this as structure new here, and then I'll go back to my folder and try to find structure new journal file. So I'll open this up and I'll save this as a Python file so that I can have the highlighting. And so there are some imports in the beginning, and then I have some commands that will do the actions I just did. So we started with a constraint sketch. We created a rectangle with using 2 points. The rectangle had dimensions of one in the width and 1 in the height. So one thing we can immediately do is parameterize the width and the height to be let's say still 1, but we can put those as parameters here. We can put the width and the height. This command has to do with essentially creating the part and then associating the sketch for the square with that part to make actually the part a 2D part that I defined. And then Abaqus decides to delete that sketch. You can choose to keep that command or not. So this is what these commands are doing. They're creating the square. The remaining commands, the commands below this, are creating the circle. So let's also go ahead and make the circle over here with a radius of 0.1. So circle center perimeter is the command that Abaqus is using to create the circle in this case. And I'll go here and change the radius to R, so I can go ahead in my script and change it every time I want to change that. Creating a part for the circle with the title part 2, and it's associating that sketch with that part to make the circle in the following 2 commands, and then again deciding to delete that sketch. So I'll put some comments here for me to help me here, which is creating square. Here I'm creating the circle, and then creating instances below here, right? So it's creating a coordinate system, a Cartesian coordinate system for me to work with. And as you can see, it's creating an instance of the square and then 3 instances of the circle. And then it's doing the translation operations that I just did. So this is interesting. And then it's performing the cut. So let's see if we can make more circles, start to essentially parameterize this a little bit. Let's say we have a variable for the number of holes in the x direction and a variable for the number of holes in the y direction. And let's say this is equal to 4 and 4. I'll come down here. This is creating an instance for the square, so I'm not going to touch that. I'm going to modify this, creating circle instances, right? So I need a for loop for that to create this efficiently. So for the holes in the x direction, for the holes in the y direction, I am going to need a name because every instance needs to have a unique name. So I'll call this part 201, and I'll go over here, format, let's say I, j. So every instance will have a unique name. And I'll go over here and create a new instance, dependent, yes, with the name I just defined. And the part will be the same. It will be part number 2. So I'll stop it here to see if this works. At first, I'll delete the other commands, and I'll also comment out the translate commands for now. So if I run this, I put number of holes as 4 and 4, so I expect 16 holes. So if I run this and it's successful, I should expect to have 16 instances with the square, so 17 in total. So let's save this and run it again. So I'll also, I'm going to put this command here in the beginning that empties the model database, so it starts from scratch. So I'll go run script, structure new. So it created my square, it created the circle, and if I go in the assembly as I expected, I have 17 instances. Now, it doesn't look like I have 17 because all 17 or 16 of the circles are in the same location. I haven't moved any of them yet. Uh, but this is going to give you an idea of essentially how I am starting to script my way through a model like this. Now, I've already done this exercise for you, and we will provide the script at the end of this class by the end of next week that does this. And I want to run it a few times so that I can show you the beauty of everything I just said in the beginning. Before we end this webinar and go ahead and answer some questions. So I'm going to put break here, something to force my script to stop here before actually running a job and waiting for it to complete. I'm going to run this script over here. Metamaterial.py is the name. So I run it. It's doing a bunch of things and it's stopping with an error exactly where I forced it to stop. As you can see, it's creating this structure. Let's open up our script again to see what it did. It used some X and Y, some width and some height, and it used a number of holes, and it used a certain radius for the hole. Let's change this to 5 in the X direction and 7 in the Y direction, and let's also make the hole a little smaller and run our script again to see if that's going to change. So I'm going to run our script again. As you can see, it created a totally different geometry. What's nice about this though is because I made my script carefully as I was going through this, if I expand my part, you're going to see that, we have sets defined, we have sections assigned. In the step, we have boundary conditions, fixing the bottom surfaces and the top surfaces of this ready to be compressed. Um, as you can see, these sets and surfaces were automatically selected by our script. So this is all being taken care of automatically and very quickly, as you saw when I'm running my script. So this is the beauty of this. Every time I run my script, these things are happening automatically. Now, this is a pretty long script. In 300 lines or so, however, I'm able to make this geometry fully parametrically for any number of holes, any width, any height. I can change my mesh settings. I can change how much I want to compress it. And even better yet, as you can see at the end, I haven't shown you this, but it's part of my script. It's actually running the job and waiting for the job to complete. And after that, it's opening the output database and it's extracting the force versus displacement relationship for me. So I've already done this in the background for you, and you can see that it's creating a file force versus displacement out, which if I open it, you're going to see that it has force versus displacement information in here that correspond to the file I just run. So this is what you can expect by making a script that creates the geometry, runs a job, and does some post-processing as well. And as I said, we will provide this script to you so that you can either study it at your own time or use it to make something that's more appropriate to your workflow. We will also provide course notes with the conclusion of this webinar that go far more in depth to what I had time to cover in those 15 minutes for you today. And we do plan to have future offerings of this class. That it's going to be the same introductory class as the one you've just attended, but also going much more in depth. This is going to be a different class that goes much more in depth into Python scripting with more advanced things that you can do. So look out for information about this class perhaps later this year if you're interested in that. At this point, I will stop because I probably covered through a lot. Depending on your background and prior experience with Python scripting, this either might have been super trivial to you or hopefully helpful to some amount and to some extent. So I'm going to stop right here and accept any questions, hopefully answer any questions that you might have. Anything, please don't hesitate to ask, either by unmuting yourself and asking now or putting them in the chat so that I can answer them as I read through them. So I'm going to go ahead and read through what we have already, and in the meantime, if you think of something that you want to ask, please go ahead and ask it. Um, I see a question here that says, how to search for any new command in the API. Can we get a list of all the methods for an object available? This is an excellent question. I'm actually going to show you a way to do this right now, a way that I find particularly helpful is going through this user interface over here can be a very good resource for you to uncovering what's available in the API. So a command that I've been using all this time was mdb.models, and I'm using autocomplete to go to my model and my part. Let's say this part, and I press dot at this point, and I want to see what's available. So what can I do with this object, right? I start pressing tab, and as I keep pressing tab, it's starting to give me, all the available functions that exist. I keep pressing tab, and it rotates through them, right? Everything, remember, everything that's starting with a capital letter, it's like base, shell, revolve, it's making something new. So it's allowing me to create a new shell. If I move forward, some new operations over here, um, tons of commands that I have available to me. So a way that I can put this is like tab is your friend in that if you navigate to what you a particular thing in your model, let's say I want to go to the sets. I want to get the edges, for example, or the elements or the faces. I'm pressing tab as I do this. Instances, nodes, reference points. There's one that I particularly like. So if I go dot edges, for example, this is a list of edges. So if I press enter, actually, if I assign this to a variable over here, there we go. It has a bunch of edges in it. So if I access the first one, over here, edges 0. There is a command that I found just like this called point on with a tab, point on, uh, that is giving you a point on an edge. Now, the reason I like this particular command and why I think it's very helpful is that if you have a geometry like this, oftentimes you need to do, some pen and paper calculations to find what are the coordinates of this point on this circle. Obviously, you can figure it out, right? Like it's not super difficult to find what are, the coordinates of a point on a circle. But this way, if you only care about, figuring out where an edge is in space, Abaqus has that built in. It just, you go to the corresponding edge if you know what that is, edge number 0 or edge number 10, and you do point on, and it's automatically spitting out a random point on that edge, which is very helpful. So this is a way with the tab that I like to essentially explore what's available on the API in here. Another way, obviously, would be through the documentation, but that can be, I guess, a little bit more advanced because it might be a lot if you're just getting started with Python scripting and you go to the documentation. The resources for Python scripting might be too much for you to make sense of, but it's always a good resource to keep in mind. So there's a question here that says how to extract output file. Last part, So I didn't cover this in detail as part of this intro webinar. Um, but very, very quickly, how did I get these commands? In short, I got these commands um, in you can get them one or two ways. You can do the macro manager uh, that I just showed you earlier. So I can go ahead and do macro manager create, and I'm recording. And now I'm going to go ahead and open. Um, I'm going to open an ODB file. Let's say I'm going to open this one, and let's say what I want to do is um, um, let's say extract the strain energy and save that to a file. So I'm going to go here, save the strain energy as is, and then I'm going to do report XY. This window opens up. Sorry. Oh, okay, it saved it like this. So then I'm going to, oh, I didn't even record it. So let's do it again. Open the ODB, and then export the strain energy, which is, I had it and I just lost it. There you go. Strain energy, save it, report XY, Abaqus 2 RPT. Stop recording. It had a problem with macros, but it still wrote the macro number 4. If you recall, we were at macro number 3. It's still outputting commands over here that I can use the same logic to go through them and clean them up and help do with them whatever I need to do. That's one way. Another way is, if you look at the commands I had in this file that I'm going to share with everybody, uh, the good thing about history output is that history output is already, in your ODB. So the only thing you have to do is navigate to it and just extract that information. So I already had a reference point for which I requested history output in this case. So I just navigated to the proper step, the proper, this node assembly 1 is the reference point I had selected, and I requested the displacement and the reaction force. And then I just converted the output to a more friendly format for me to export in a TXT using NumPy. So if I go back to that file or to that folder, I'm sorry, you see the way I exported things with Abaqus was like in this form. It has a header. That's one way to export things. The other way that I'm doing it, it's more convenient for me, but might not be for you. It just contains only the information that I need. It's X for displacement, Y for force in this case, and that's it. So you can use, in short, to answer that question again, you can use everything we showed up to this point to to figure out how to do post processing. So the macro manager still works. We still got 2 minutes, so if you have any additional questions, please go ahead and ask them. Um, that's great. If we don't have any more questions, in a minute, I'm going to end this session and end this webinar. And before I do, I want to thank everybody for attending. Um, please keep in mind that this is just a pure introductory webinar to hopefully shed some light on how to get started with Python scripting. Again, thank you for registering and for attending. We will reach out with a PDF link to the notes, the course notes, for everything we covered, plus some additional things for this class. and we will also send you the Python script file. And please keep an eye for future versions of this webinar that are going to go much more in depth, hopefully teach you a few more things that you need to know, or other webinars that Varist is offering that you might be interested in that I covered earlier. Reach out to our website to find more information. Thank you all for joining. I hope you have a good rest of your day. Again, thank you.